Okay, thank you. Yo, Camus. Right. So we just talked briefly about computer networks. We know that there are small networks, there are large networks. The smaller ones are known as local area networks, and the larger networks are known either metropolitan area networks or wide area networks. Oh, here. Right, guys. So we said whenever a communication is needed, we need a transmitter and a receiver to carry the signal that represents the data. Now, the transmitter will transmit, will put the signal, and the signal will be carried by something we refer to as the medium or media. So the media that's used in computer communication and in most communications, there are generally three types of media. Either cables that connect computers and devices together, or transmission by wireless means like radio, electromagnetic waves. We call them radio waves or electromagnetic waves. So transmitters that transmit the signal and a receiver that receives it at the other end without using cables. And these are usually known guided or unguided media. So if the signal is placed on a wire or a cable, it will follow this wire. And therefore it's called a guided media. The signal is guided through, it has to follow this particular wire. If it's a radio transmitter that transmits a signal in all directions or broadcasts it without having a wire, but actually having an electro transmitter, and if you have an antenna somewhere, you can receive that signal. They call this unguided. So all signals that are transmitted are either transmitted as guided or unguided signals. That's just one way of classifying how a signal is how the transmission is classified. But when we talk about the media, the first type we talk about is an electric wire, and it's called the twisted pair. Twisted pair. This is the first type that was used to carry data. And it's a metal wire, pair of wires that form an electric circuit that goes around between the sender and the receiver. It has been in use for the last 150 years in the telephone networks, and computing started just using it, and they tried to improve it a bit. So anytime there's a computer, two computers connected or more, there'd be a wire between them that forms an electric circuit, and the current flows from one to the other. And every electric signal has certain characteristics. It has voltage, you can measure it. It has frequency, we can also measure it. And we change those in order to represent data from the sender to the receiver. So remember, anytime a generator works, the way electricity is generated, we don't need to go through it, but it's good to understand it. If you have a magnet, there's something natural that happens. If you have a magnet, a north and a south pole magnet, and if they're close to one another, and you take a wire and pass it through them, you know what happens naturally? Current flows through the wire, and that's how electricity is generated. So electricity is generated by having a north and a south pole magnet. They're connected together, and they kind of magnetism flows from north to south or vice versa. And if we take a wire, usually you take a wire like this, and we pass it through them, just through them. And they usually rotate it. So if you have it rotated, and the wires will be going between the two magnets, electricity will be flowing in this coil. So that's how all generators are made, and also electric motors. So these are the two kind of events that naturally occur. If you move a wire in a magnetic field, it will generate a current in it. That's how electricity is generated. So that's one thing. So in order to generate it, as the wire, for example, if these are the two magnets, one on each side, as the wire goes across between them, the more their magnetic lines going from north to south, as the wire goes down near the magnet itself, it crosses more magnetism, and it generates higher current. And as it's moving from one to the other, at this point here, it's not crossing any lines, it's going with the lines or through the lines, and therefore it generates less electricity. So if you measure the actual current, it's not always great amount of current going. It gets greater when the line is crossing near the magnet itself, and no current is generated as it's moving with the lines of magnet. So remember, magnetism between two poles, magnetism is flowing in this direction from north to south. If this wire is going with the magnetism, it's not crossing any lines, so it doesn't generate any current. So if you measure the actual current generated as the wire is rotating, and if we plot it on a diagram, say provided this is 0, that's 5 or 10 or whatever the maximum, you'll find that as it goes from this point, it's crossing no lines, so it's 0, but as it's going up, this is the maximum amount of current. So if you keep measuring it, you'll find the highest point is at this point here. And then it will start going down again, and it goes down to 0 again. So if we do this over time, whether this is every 1 second goes up, another second goes down, another second it go past this line again, but because it's instead of going up, the wire on this side going up, it's going down, it actually generates current in the opposite direction for some reason. So, and they call that the negative kind, and it gets down to the maximum point here, so it's -5 at this point and back to 0 again, and the cycle keeps repeating itself. So as a generator is rotating, and they rotate quite fast, you get a lot of frequency. If you keep measuring those voltages or the current, you'll find that it keeps going up and down all the time, increases to +5, -5, +5, or -12, +12, whatever, depending on the strength of the magnets and how good the conductor is, you get more current going in. So that's the basic idea of generating a current. Now, and they call this a cycle. Every time it goes through one full revolution, the cycle gets formed. So how fast does the generator rotate? It can be 100, you can generate 100 cycles per second. or 1,000 or more or less. The thing about it, we can easily measure the voltages, how much voltage or how much current a generator generates, and we can also measure how many cycles it has every second.
So on the left, well, left to me, the drawing of the north and south.
Yeah.
What is actually going around? Is it like electrons?
Wire. A wire that goes around like this in like a box, and we just keep rotating. So the two sides of it keep crossing, one cross on this end and one cross the other end. So current is flowing through this wire, what they call the coil. Okay, in electric motors and generators, if you open one and look at it, you'll find a very long wire is coiled so many times. The more wire you can have between the magnets, the stronger the effect is, the more current is generated. You don't need to know the details, but this is the basic idea. This is a fact. This is a natural thing that happens. Anytime you have magnets, you take a wire, pass it through them, current will flow. So if you complete this wire in a circuit, you can actually generate a light to light a bulb, or use that electricity. That's how electricity is generated. In dams, all they have in water dams, they have the water rotating this generator that has two magnets and a coil between them. And as it rotates, it generates electricity, and you can use it at home. So this is the basic idea. And they make it stronger by actually, instead of having two poles of magnets, north and south, they might have another two on either side. And they might have more magnetism, more magnetic poles around it. So it actually generates even more electricity and has higher cycles. So that's one fact. Anytime you move a wire through magnetic field, it generates an electric current. The other fact is the other way around. If you have a current going through a wire, it will generate magnetism. So these two things happen. For example, if you have now that wire, if we have an electric circuit between two computers and current is flowing, like we have current flowing in a circuit, in an electric circuit between two computers. As current flows, it's also a natural thing that happens, that it actually generates a magnetic field around it. You can't see it, but it actually generates magnetism. How do we know? If you bring a compass beside this magnetism that normally points to north, you put it close to this wire that carries current, it actually generates magnetism that it will actually pull the compass towards it or away from it. Instead of pointing at north-south, it will point at this magnetic field. So these are two natural phenomena that happen, and us people use them for our benefit. So the two phenomena. If you have magnetism, you have a wire pass through the magnetism, it generates electricity. That's how all electricity in the world is done. All we do is have a wire rotating inside a magnet. How do we rotate it? We rotate it by air, we rotate it through water in dams, or we rotate it by an engine that runs on petrol. That's how all electricity is generated in the world. That's one phenomenon. The other one, the opposite. If you have electricity flowing through a wire, it's generating magnetic field. And it's like radio magnetic transmission, like a radio signal. Yes, that's what it is. They call it the electromagnetic signal, the radio transmission. But that's the basic idea, is that if you have any wire with electricity flowing through it, not stopping, not static, it's actually electricity is going through it, it will generate a magnetic field. How much magnetic field? It depends on the strength of the current. If it's high current or high voltage, the magnetic field will be a little bit bigger, and if it's low, it will be reduced. And you can actually sense this by compass, but you can also, there are special devices like antennas, like radio antenna, pointed at this magnetic field, and you can actually pick it up. And in fact, that's when we have wires carrying our data, our communication, they actually generate magnetic field all the time. And there are devices, and you can buy them. They're available. You can put it beside the wire, not even close to it. Even they're so sensitive, they can pick this magnetic field that's generated. And then we have applications or devices that can transmit that magnetic field. Say, okay, this is a high magnetic field. That's probably, they're sending one. Remember, every time we send data, we're already sending 1 or 0, but there'll be millions of them. And we can actually pick it up, pick that signal that's flowing through a wire, through the magnetic field by an antenna, and we have a little computer that tells us, oh, that's high, it's 1, 0, 0, 1, and we can actually, all the information you send through a wire, you can pick it up without touching the wire. So just to let you know, communication is not secure. Anytime you send a message, if it's wireless, then almost everybody gets it. If it's through a wire, through an electric wire, electric wires are not secure. They actually, it's like carrying information and telling everybody, this is the information I'm carrying, this is the information I'm carrying. That's what they do, actually. And if that information or the company is important enough, then there'll be other people who are actually outside. Remember, all this campus, there's one wire that connects us to the outside world, maybe 2. So they find out where it is in the street, and they can park a car and pick the information. So all the information leaving this company or any other organization or company can be picked up by competitive organizations if they want it. Okay, so these are the 2 little problems that we'll face. So remember, anytime electricity is flowing through a wire, it's generating magnetism. And every time you have a magnet with a wire in its vicinity, magnetic field with a wire in its vicinity, then current is flowing through that wire. And these both are problems. Why? Because that's how we actually send data in what's known as the first type that carries our information, the first medium. It's called twisted pair. And twisted pair is just a pair of wires connected between 2 computers, but they actually twist them around. And we'll see the reason why they're twisted. But for now, that's the way it works. A twisted pair carries a signal all the way from one computer to another. It's used for computer networks. So we can either connect multiple computers to the same wires or connect another computer to this wire, and they all get the same signal. Signal is always flowing between them all. And that's how really local area networks is the most used form of a medium in computer networks. It's called the twisted pair. Why is it used? Because first, twisted pairs or electric wires have been around for a long time, being used by the telephone organizations and companies on phones, and they're available. They've used them, they manufacture them, they cover them with a little plastic to insulate them, and they're available and they're cheap, very cheap to buy. Meter for meter, they're very cheap, maybe 20 cents a meter or 30 cents a meter. You probably get them even cheaper in many different countries. And we always we put a special end at the end of them, fitting, and that's just a plug that plugs into the computer. Are they good? It depends, again. Let's look at other alternatives, and then we decide, compare them. And the other alternative is something called fiber optic. So this is the second medium that we look at, fiber optic cable. A fiber optic cable is again a wire, but it's not made of metal. It's made of glass. It's a little thicker than a human hair, maybe a few hairs put together. So it's fairly thin thread of glass. And it can break very easily, it's fragile. And for that reason, when they manufacture it, they mix it up with a bit of pure plastic, very high quality plastic, just to give it a bit of flexibility so it doesn't break as easy. But they don't want to lose the glass kind of effect in it that carries the actual signal. But signal in fiber optic cable is not sent by electricity. So what they do, they send a light signal. So it's like light. They send a beam of light, like flashlight. It's a laser, low beam laser or flashlight. So instead of sending an electric signal, your computer will generate, so all computers at this stage, they generate electricity to represent the signal. So we're sending 1 or 0. You get high frequency, high voltage, low voltage. But what we do is convert it from electric, we turn it into light. So it's just like a flashlight. You get battery current, electric current, you turn it into light. How strong is the light and what's the frequency depends on the input. So the light will have frequency as well. So which frequency? There'll be 2 different frequencies based on the electricity that comes in. So instead of sending 2 frequencies on an electric wire, we do the same, but we do it on light. And if you change the frequency of light, you actually change its color. You know, when you see the different light, you see blue light or red or, you know, all the different colors that we can see are actually light at different frequencies. Not that it's important to us, but the good thing is that light also travels in frequencies, just like electricity. And frequency is the number of cycles per second. How many, you see that cycle that we made with electricity? How many cycles every 1 second? That's what the frequency is. So, light is flashed into the end of one of the wires, one end of the wire, and goes, sometimes it hits the edge, it's reflected back, hits the other edge, reflected back, keeps reflecting until it gets to the end. Even if the wire rotates, it will follow, light will follow. And at the other end, there's a light sensitive cell. You know, there are cells that are sensitive to light. And once you get the light, it generates electricity. So the other way around, here we have electricity, it generates light, goes through the wire, the glass, and then at the other end, we receive light, convert it back into electricity. And then we find that it represents 1 and 0. So this is the second medium that's used for delivering messages. Now, which one is better? A twisted pair. The twisted pair, the electric one, so this uses light as the actual signal, and this one is electric. And the 2 wires are actually twisted, rotated around each other, twisted around each other. That's what a twisted pair. Now, first, why do they twist this wire? Because when they used it first, it was straight wire, just a pair of wires that are straight. But remember, we said there's something that naturally happens. If those wires are beside an air conditioning unit, AC unit, or a washing machine, or any machine that has an electric motor, when you switch the motor on, every electric motor, when you switch it on, it takes a lot of energy to get it to rotate at the start, and that energy radiates a lot of magnetism. If you have a data wire, if we have a wire carrying our computer information, and this wire is beside this machine, the air conditioning, every time you switch it on or off, it kind of lets out a big puff of magnetism, and that magnetism going through the wire, do you know what happens to the wire? When a wire is in the vicinity of magnetic field, it will generate small current in that wire. That current, as well as the current that we are sending with the data, it will ruin that. It will mix it up. So it becomes like noise. So the receiver doesn't actually understand anything. Okay? So it's like us talking and somebody outside to boom, make this huge noise, or maybe, you know, shoots a gun or something, there's a huge noise that you don't understand anymore what one is saying. Or somebody starts screaming out there, that's another audio noise. But for electricity and magnetism, if you have your wire running, carrying the data with nice signal, but then this magnetism beside it generates extra electric current, it will mix this information, and we call that noise. So this happens in electric wires. So electric wires can have noise. Magnetic, it can be affected by any magnetism. The light never gets affected. So the light signal is very, very clean. That's one thing. So this comparing now, is it better to use electric wire, that we call twisted pair? And the reason why, by the way, they twist it, because a straight line is a very good receptor to magnetism. That's why your radio, for example, if you drive a car and you have a radio and there's an antenna at the back of the car on top of the roof of the car, it's a straight wire that receives a magnetic wave from the radio station and goes across this wire and generates a small current, and that's brought to the radio station, amplified, and you can hear the actual signal, turned into sound. But that antenna is a straight antenna. If you break your antenna and twist it again, it will be a bad antenna. So that's why they say with our wires that we use for transmitting data, to reduce the effect of them receiving signals from radio stations and from magnetic fields and machines and air conditioning units, twist them around. Because a good antenna, a good receiver, is a straight wire. But this is not, we're going to make sure that our wire is not straight, and therefore it will not receive noise in magnetic form from other, magnetic sources. So that's why they twist the wires that are used for computer data. The reason? Do you know what the reason is for twisting the wires? So to reduce the effect of noise, magnetic noise onto them. If they were straight, they'd be very bad. They'd be good antennas, but that's not what we want. We don't want them to take any current from the outside world, from any magnetic charges, any machines or radio stations or anything. So that's the reason why they twist it. So all wires that are used for, electric wires used for computer data communications and networks, they always twist it. You see them, and there's a reason. And that's one of the reasons why they have them twisted. But now, comparing those two, remember, electric wires, as we send signal, they radiate. They radiate, they generate a magnetic field. Every time you send your message, they start generating the magnetic field, which is bad because your competitors can pick it up. So I just write the key words that I'd like you to remember: radiation or radiate. Do they radiate? Light does not radiate nothing. You just send a light signal, one beam of light going through glass will never create a magnetic field. So light is more secure for two reasons. It doesn't radiate magnetic field, and it also does not get affected by noise by magnetic field. So even if there is a magnetic field here, north and south, there is no effect. Clean. Light does not get affected. So if you're asked which one is better, an electric wire or a fiber optic wire, what do you think is better? Which one is better? Which one would you prefer? Electric cable or a fiber optic cable?
Well, it depends what, of course, what.
Yes. So you need to say, well, in the case of, from a security point of view, the fiber optic is better because it does not radiate. Nobody can tell what's that signal that's going through the wire without actually, getting the connection from the wire, but not by radiation. With twisted pair electric signals, all electric wires, as they carry a signal, they radiate a magnetic field. You can't see it, but you can actually pick it up. So from a security point of view, twisted pair is not secure. Why? Because it radiates. Also, electric wires can be affected by noise. That's by the magnetic field outside it. It will create noise in it. So if you're sending your data, maybe every now and again you'll get some noise. So the packet is gone. So you have to, maybe the sender have to retransmit it for some reason. Fiber optic doesn't suffer from magnetic noise. It has no magnetic noise whatsoever. So fiber optic has the cleanest kind of signal, and it's the most secure in those two. Right, what else? There's something else called attenuation. Attenuation is the weakening of a signal over distance. What you also need to know, any signal that we send, audio signal, like when I speak now, when I'm not speaking, I'm screaming. When I scream, those you can hear me very well, and then the scream goes a little weaker. The person at the very end maybe doesn't hear me as clear, but maybe if we go another 50 meters, he won't hear me at all. So every signal that we send, we generate, it starts getting weaker as it's traveling through air. Also, if it's going through metal, like electricity going through a wire, it gets weaker because the wire is resisting the signal going through it. Like you swimming in a river, let's say in the opposite direction. You swim, you start making few gains. You have enough energy, you start going. And the water starts pushing you back, resisting you, and then you start losing energy. After a while, you become so weak you can't go any further. Exactly the same thing happens with electric current going through a wire. The moment it starts moving, the wire is resisting it, but it still has a lot of energy at the start. So it keeps going, the electric signal keeps going up to a certain point, and then it can't go anymore, it cannot be recognized. Same with audio signal, same with light signal. Everything, wherever it travels through a medium, it meets resistance, and it has a certain range, and that range is known, or this feature is known as attenuation. So attenuation, if you ask what attenuation is, it's the weakening of the signal over distance. Not the weakening because of another reason, because maybe the power source is diminishing, no, it's for traveling. As the signal travels over distance, it starts becoming weaker. That weakness, we refer to it as attenuation. And attenuation is important now because in communication, we want to talk over distances. Can our signal travel? We don't know how far. But with twisted pair, when they started first, do you know what the range was? 10 meters. Yeah, not much. And they used copper. Copper is a very good conductor. Copper wire, small, thin copper wire. And then they started mixing them. Different companies started trying different combination of different metals. They call them metal alloy or copper alloy. That means copper mixed with other metals. With certain percentages, in certain ways and certain treatment, they started improving this. The signal started going further. At the moment, they have it up to 100 meters. So at the moment, the longest signal you can use twisted pair for is 100 meters. So if you're asked what's attenuation for copper wire, it's 100 meters is your range. After that, the signal is too weak, it cannot be recognized. Of course, after a while, you can fit a device that we call a repeater. Like normally, if you send a signal representing ones and zeros over a distance, the signal will go like this. We send it, for example, +5 volt, for example, and -5 volt. These are close up, very close figures to one that they actually use. Maybe this one to represent bit 1 and -1 to represent bit 0. So if I'm sending 1 1 0 0 0 1 0 1 0 0 1 0 1 1, it'll be like this. We'll turn the voltage up, the sender will turn the voltage up to plus, stays plus for another period. They go down to -5, and then up for this one here, the 1, and down and up and down, and down, and so so on. So this is the way you'd see the signal, ideally. So the receiver, anytime it got any part of the signal, it can say, oh, that's -5, that's a 0. I'll write 0 in my memory. That's +5, I'll write 1. That's how we send data. Remember, we never send actual data. It's the same signals going, just increase voltage or decrease it. But in reality, over distance, this lovely signal will probably go like this. It'll start strong, but then start losing the edges here, the corners, and start forming like little circles. And then it starts losing the height as well. Instead of going up really high, it starts going like this, weaker, and then becomes unrecognizable after 10 meters or after 100 meters. But what we can do, well, what they do in network is here where you can still recognize it, even if it's +1 and -1, you can still say, oh, that's the positive and that's negative, that represent bits, ones and zeros. At this point, they put a device that can still sense and then issue a new signal. You say, oh, are you 1? No, I better send 5, +5. Are you -1? I will send a new fresh signal, -5. And they call this device a repeater. A repeater just takes a signal that's weak and generates a new fresh signal, but still recognizable. So it identifies that, oh, this is a positive, this is above certain value, above 0, I consider +5 maybe, and below 0, I consider -5. So I generate a new signal based on that signal. And therefore, we can bring this signal, instead of 100 meters, can bring it to 200 meters. You can put another repeater. A repeater is just like an amplifier, but that makes expand the signal. But amplifiers are used for the old, digital signals, non-digital signals. And repeaters are used for digital signals. The analog signals, the old system, they call them analog signals, that have any value. Digital signals, they only have 2 values, representing 1 or 0. It can be +5, -5, or 5 and 2, or 5 and 0. Any 2 values, we agree, one representing 1 and one representing 0. We call it digital. So anytime you hear the word digital, it means 2 values. On computer language, that's the 1 and the 0. So we can use any signal that can take only 2 values. But other normal old radio stations and old recordings, and when you speak and you record it, comes out as analog signal. It can have lots of values, 3.1, 5.7, 3, 2, 2.5. That's called analog. So analog signal has lots of different values. Digital signals, only 2 values. That's why if you see any other value other than those 2 in computer, in digital, you say, oh, that's noise, get rid of it. So you can actually clean digital signals. Why? Because we know there should only be 2 values. But the other analog signal, let's say somebody's talking and then you get this peak, voltage went up to 75. You say, is that noise or did that person just scream at that moment? You don't know, but in digital we know. It can only be 2 values. Do you have a question?
Yeah. Do they put repeaters on all the telephone poles? Is that like what those are?
Yeah, well, yeah. But when you get to a switch or a router, that will generate a new signal of its own. So it doesn't have to be at every location. Only when there's no repeater, there's no device transmitting in the signal. Maybe if we have a local area network, we have all our machines here close in this room, we can all reach them, but we have 1 or 2 machines on the other side of the building. That's more than 100 meters. So we might need a repeater or 2 to reach them, to include them in, to become part of our local area network. A repeater in other technologies can be one on top of one building and the other one on another side of the building. Radio stations use those repeaters. A radio transmitter usually might have a range of, say, 20 kilometers. After that, no, there isn't. So what they do is they have at that, near the edge, they have one device to transmit a signal to another device there, about 50 kilometers away or whatever it is, and that then will transmit another umbrella kind of thing. So those 2 devices send it from one area to the other, they call them repeaters. And yeah, many times in radio transmissions in countries, they might have multiple repeaters to cover the entire country. But that's on wireless, and that's more than 100. Wireless can go kilometers, you know, like 20 kilometers or 50, it depends on the transmitters. But not on our computer communication. Computer networks, they send very little current, 5 voltage maximum. So, you know, it's not dangerous to touch, and it's, you know, but it doesn't go far. That's the maximum. It goes 100 meter if we use twisted pair, but we can use repeaters. Now, let's go back to this signal, to this image. Now, fiber optic. So we know what attenuation is. I have this friend here. You know what is attenuation? You know the term attenuation? You want to tell me? Attenuation. Yeah, it's the weakening of a signal. Guys, stay with me. I'm talking to you. I want you to interact with me. You know what attenuation is? Okay, good. Right. Now, what's the attenuation on fiber optic cables? Anybody knows? Remember, twisted pair, it's 100 meter attenuation. On fiber optic cable, it's about 60 to 100 kilometers. Kilometers, not meters, right? So, if you have a really big network, or if you want to connect to another office somewhere else, or you know, another station, if it's up to about 50, 60 kilometers, if you use twisted pair, you're going to have so many repeaters. If you use fiber optic cable, you don't even need a repeater. Right, okay? Are you with me there? Stay with me. So, do you know the attenuation on a fiber optic cable? Yeah. 100 meters.
60 to 100 kilometers.
Yeah. So on fiber optic, the light cables, the range is much longer before the signal becomes too weak. It's about 60 to 100 kilometers. Remember these, because these are the differences when you say, oh, we better not use, you know, twisted pair. Fiber optic is better. When? If the range is big, if the, you know, bigger than, and we don't need to use repeaters, probably works out cheaper. Yeah?
What do you use instead of repeater in fiber optics after 100 kilometers?
It has repeaters as well. Another device that takes that light signal while it's still recognizable and generate another one, a fresh one, and send it across.
So both are different devices, right?
They're different. The one is for electric repeaters are different to fiber optic repeaters, completely different. Right, something else. So, as you can see now, which one radiates? Fiber optic cable or twisted pairs? Which one that radiates, generates magnetic field? Twisted pair, and therefore it's not secure, it's not good. Which one is more affected by magnetic noise? Twisted pair or fiber optic? Fiber optic doesn't get affected by any magnetism. The signal is always clear. It has less noise. Right, and it has longer range. Attenuation is much longer. Now, if we have our, like the place where we need to deliver data, it goes through a sea, or, you know, a pond, or some water, lake or river, across the water in the river. Which one do you think will last longer? Twisted pair or fiber optic? Why? What happens to twisted pair? Any idea? No, let's say the distance is not that far, but it has to go through water. Okay. Twisted pair is made up of copper, and copper will rust, will corrode, will disintegrate if it's played in the sea or in an ocean or in water or humid place. So the environment, which one is better with the environment and can resist the environment, is the fiber optic. Glass does not corrode, does not rust away. In fact, the first glass cable, fiber optic cable that connects Europe with America was placed about 50 years ago, 48 years ago. It's from here, the west of Ireland here, all the way to the eastern coast of America to carry information. And it was just an experimental thing. See, at that time, back in the 60s and 70s, there used to be something they used to call Cold War. You probably heard of it. Yeah, we still live in it.
We use it to be,
Yeah, and mostly between Russia and America, or Russia and the West, including Europe. And this fiber optic actually was the development of that as well. These two countries were so crazy. Now, every one of them had obviously lots of nukes, like nuclear, and they were worried the other one is going to bomb us, right, and destroy us, so we better be ready. And they're always thinking there's a war going to happen, there's going to happen, that war is going to happen. And they build a lot of arms and a lot of nukes and all that. They got to a point, they said, okay, armies need communication. And guess what? America and the West were better at communication. They had more satellites up in the sky, and they were communicating a lot better. But Russia said, okay, that advantage, what can I do for it? And they said, right, one nuclear bomb, not on America, but somewhere in the ocean between America and Europe, up in the air, and it blow away all these satellites. They'll all be disappearing. And that will terminate the communication between Europe and America. And it's true. The Americans and Europeans realized, oh, that will destroy the communication, the advantage they have. So they said, we better have or think of a standby project. And fiber optics was just coming out. They said, okay, so let's have a fiber optic communication cable laid between Europe and America. And that was the first fiber optic cable to be laid under a sea or under the ocean for the purpose of communication. It was for testing, and they put it down back in 1976. And guess what? It's still there and still carries more than 80% of the communications between America and Europe. It carries more TV channels and more TV communication and telephone communication, computer network communication, and hasn't rusted away, hasn't broken, hasn't disintegrated, and it's just proved to have huge amount of data that you can transfer through it. And now, in fact, fiber optic cables, there's so many fiber optic cables connecting all the continents, all the countries in the world under the oceans. They are really carrying most of the communication, most of the television transmissions goes under the ocean in these fiber optic cables. Why? Because fiber optic cables, they have another advantage, and that's something called the bandwidth. And the word bandwidth means how many, the exact definition is the range of usable frequencies. The range of usable frequencies. What does that mean? Now, we said if there's a user here and a user there, and we have a wire between them, an electric, of course, wire, and this guy wants to send a message. That's ones and zeros. All our messages are ones and zeros, wants to send it to the other side. We can use frequency. We said we can change the voltage, but we can also change frequency instead. It's actually frequency is even more used. So how does frequency work? We say, right, for example, you have an electric signal that has frequency, for example, 1 million cycles per second. 1 million, say, this is a low frequency, slow frequency. This is a really high frequency. Just how many times does it cycle every second? So they found that we can change the frequency. It's so simple. It's like you have a fan. You can turn it high or low or medium. But this one with electricity, you can change the electricity, how quick it cycles. And So if we allocate 2 frequencies to this guy, we say you're 4 million cycles per second and 4.5, for example. One to represent the bit 1 and one to represent the bit 0. Any 2 frequencies. So I'm sending you a signal and I want to send you 1 zeros, 1 zeros. So if look, oh, I'm going to send 1. Here's the frequency for 1. Here's the frequency for 0. And you can sense that. The receiver can sense, oh, the frequency went up, the frequency went down. They can actually read the exact frequency. So one communication needs 2 frequencies. Right. Then they went into sending 2 signals on the same wire, or 3 or 4. How comes? Now, for example, this guy A is talking to B, and we gave them that frequency. Let's say now another user called C wants to communicate with D on the same wire. We can give them 2 different frequencies. You can say, hey, you can use frequency 6 million cycles and 6.5, for example, to represent 1s or 0s. So both signals will go, this guy is sending this signal, and those here are sending this signal. And guess what? We can use 1 wire and we can send 2 signals on it. As long as they are not the same frequency, we can separate them and successfully without interfering with one another, without any noise. Right? So now we can use exactly the same way as radio stations. Remember, the air is full of radio stations sending their signals. And you can select, but they are all, each one of them has a different frequency. Remember, you say, you listen to one radio station, say 501, that's 501 maybe million cycles per second. Another one is 102, that's 1.2 million cycles per second. You just call it 102. Or whatever. It doesn't matter what the name is, sometimes they give a different name, but the frequency, they use different frequencies and they're transmitting them all the time, radio signals. Now, right now, your brain is getting lots of signals, but you don't care about them. But we have receivers or radio that you can pick one frequency and you can listen to one radio. Change another frequency, listen to another radio. It's the point what I'm trying to say is that now technology, you can send lots of different frequencies and successfully communicate without them interfering with one another, as long as they are on different frequencies. Now, then, okay, then what's the problem? We have 1 wire, let's send 2 million different frequencies on that wire. So we have 1 million people talking. Each one of them has 2 of them. Okay, we need to leave a bit of a gap between frequencies because transmitters are not very accurate exactly on that. So some frequencies cannot be used, just they have to be spaced between, like any 2 users, give them different frequencies and leave a bit of space of frequencies so the others will not interfere with them. Also, very low frequencies will not be successful. Very, very low frequencies don't only go for a meter or 2. And also, very, very high frequencies will not be successful to carry information. So, if for every wire, for every material, they tested almost every material. Let's send high frequency, low frequency, all the different frequencies on copper, on iron, aluminium, all those different metals. And for every metal, they found it has different frequencies that cannot be used. Very low frequencies can never be used. Very high frequencies cannot be used. So every material has a range of frequencies. So for example, if we have 100,000 different frequencies usable on this, for example, here's the high frequencies and low frequencies. This part cannot be used, that part cannot be used. Only we can use this part of different frequencies. Every 2 frequencies can be allocated to a user, so how many users can we have communicating on that wire? So, and every time as many 2 pair of frequencies you have, then you can send as many bits that you can send, but whatever the maximum number of bits the user can send. Then let's see what's the maximum number of users, 2 other users and the other user, and all the different users that can be used. We can work out the total amount of data that can be transmitted on one wire. And that's called the bandwidth. So the bandwidth has 2 definitions. If you are asked what is the bandwidth of any material, it's the range of usable frequencies. Every material you can transmit so many frequencies on it. Some of them will not travel on this particular material, and some will travel. So the ones that will travel, that is good. That's the one we're looking for. That means we can send data on all those usable frequencies. The other definition is what's just the total amount of data that can be transmitted over this medium, which means the total number of frequencies and what you can send on each one of them. So that's called the bandwidth. So twisted pair, we can send a lot of material on it. We can, because a lot of frequencies work well on it. But the maximum amount, I think, is somewhere around 100 million. So let me get, or 1,000 million, sorry. So the bandwidth for twisted pair is one giga. They start from the mega, the million bits, the total number you can send, 2 gigas. Giga is 1,000 million. That's 1 billion. Giga means a billion bits per second. That's the total you can send on twisted pair. Not in one frequency, but on all the frequencies. The total amount you can send on a twisted pair is 1 giga. Now, we go to fiber optic. They found that it goes into the tera bits. Tera means 1,000 billion. The next 3 zeros. So this information is on Moodle, so we don't have to keep writing it. But the point is, a fiber optic, one fiber optic cable can carry more information than 1,000 twisted pairs. Right? So that's as much as they can carry. So, but of course, it's a little bit more expensive to buy. You know, if you want to go and buy 1 meter of twisted pair, it probably costs you 30 cents or 40 cents, like under €1. If you want to buy a meter of fiber optic cable, anybody knows how much? Anybody bought any fiber optic cable recently? You know, for connecting your TV to whatever those, about €5, €10 on the outside. Right? But there's a big difference between 50 cents and €5. That's probably, again, 100 times, 10 times more? No, 500. 100 times more expensive. But it's more expensive, but be careful. If I say to you, which one is more expensive? Twisted pair or fiber optic? To buy 1 meter, fiber optic is going to be more expensive. But in computer networks, we don't talk about, you know, go and buy a few meters. How much data you want to transfer? The fiber optic can transfer 1,000 times more than a twisted pair. So, for example, we want to transfer terabytes of data. You buy 1 fiber optic cable, or you go and buy 1,000 metal wire. So it could be cheaper to buy fiber optic, even though it's slightly more expensive. You understand that? Good. So which one is more expensive? No. It can work out to be cheaper. Like if you go to a company and they say, hey, we're going to dig, you know, a tunnel here, and we lay down a cable all the way for 40 kilometers to our, whatever it is, or even only 10 kilometers, not too far. And we're going to send 5 terabytes of data every second. Shall we go for fiber optic or twisted pair? Go for fiber optic. 1 or 2 wires fiber optic will do the job. But if you are going to use twisted pair, you're going to be needing 2,000 wires of twisted pair or more. And of course, 2,000 transmitters, and there'll be so many repeaters, but I'm just, the cost just to buy it. So I know to buy twisted pair is cheaper, but be careful if you ask which one is cheaper. Don't say twisted pair is cheaper. Say it depends on the amount of data you want to send. If you're in a company, like we here, if we have a company, and we are a video development company, right? Video editing. So you work a huge amount of data, and when you finish, you send it to that person who specializes in color. When he finishes, he sends it to that one who specializes in music and sound. So we're all sending a lot of huge amount of data between us. Would you recommend twisted pair or fiber optic? fiber optic in this case. Anytime you hear the word video, that means a lot of data, you want to send it quickly. Fiber optic is the best. It can deliver a lot of, it doesn't deliver data faster. Remember, it uses light, and light is always faster than electricity, but not by much. Electrons fly at 2/3 the speed of light. So yes, light is faster, we're going to send signal a little bit faster, but that's not the advantage. The advantage is that with fiber optic, it's like having a motorway that has 20 channels, 20 tracks, cars are driving, 20 cars driving at the same time, and the twisted pair is like a road that only has one lane, one car is driving. They all drive at almost the same speed, the cars, but over there we can deliver 20 cars at the same time. We're here only one car at a time. You understand the difference? So it's not really the speed difference. We know light is a little bit faster, but that's not the major advantage. The major advantage is the big bandwidth. You can send 1,000 or more signals simultaneously at the same time in fiber optic cable, while in twisted pair, you know, the number is limited a lot. So one final question. Let me ask one final question. Stay with me. Is it better? Which one is better, fiber optic or twisted pair?
It depends.
Very good. Now, give me one reason why fiber optic is better. Let's say if we're going to lay down cables in the sea, which one would you go for? Fiber optic or twisted pair? Why? Because it does not corrode. It will resist the salt and the water, while copper corrodes very quickly. Do you have a question?
Yeah. So I know when you cut open a twisted wire cable, there's a lot of like wires in there. How do they not confuse each other?
Yeah, okay. We'll get to that. Let's get, usually when you buy a network cable, instead of 2 pairs, they give you 4 pairs, like 8 wires. And they have them color-coded, green, red, something, you know, all the different colors. So when you want to connect a wire on this end and you go to the other end, you don't connect the wrong end of the wire. So it's the green or the blue or the red one. So they're color-coded. But they give you 4 of them together in order to use them, if you can use them. Right, so this is a quick idea of those 2 mediums. Anytime you're asked to compare them or to make a choice, think security. Right, I'll just give you the factor, but later on you have to think yourself of those factors. Which one is more secure, fiber optic or twisted pair? I say fiber optic. I heard you saying which one is more secure? Fiber optic. Yeah. Why?
Because it's just lots of points
Why is fiber optic more secure than twisted pair? It doesn't have noise is different, is affected by noise. That when outside signals come into you, that's not security. There's no lack of security there. It doesn't radiate. It doesn't tell the world, here's what I'm carrying. The twisted pair does that, and that's why it's not secure. Okay? Yeah. Now, bandwidth. Which one, you know, if you have a large amount of data, which one would you use? Fiber optic. Why not twisted pair? So twisted pair has a very small bandwidth compared to a fiber optic. What about, yeah. What's attenuation? I have a volunteer. Okay, what's attenuation? A signal, that's not attenuation. What's attenuation? What's attenuation? Over distance. Don't forget over distance. Yes, attenuation is a weakening of a signal over distance. How do you get noise in a twisted pair? How do we get noise in a twisted pair? external magnetic field, if it's in the vicinity of a magnetic field, then it will. Right.
How do you get noise in the fiber optic?
No, it's clear. Okay, I'm gonna